Now, sometimes the payoff table does not represent profit, but rather cost. And when the table represents cost, the smaller is the better, because if the cost is like cost of doing business, the smaller number that you pay, it means it's cheaper, so it's better. And when the table represents the cost, the optimistic approach, conservative approach, and also the regret tables, all these things have a different meaning, because now the smaller is the better one. And since it's confusing, I decided to make a separate video for this case. I'm not going to specify what these state of nature are and what these decisions are, because that's not too important. Let's just think about what optimistic approach is. Optimistic approach thinks about the best case scenario for each decision. And among those best, you look at the best outcome of the best. That's what optimistic approach means. However, because the better number in this case of the cost is the smaller number, the meaning of what's best is different from when you have the payoff table. So let's look at this decision 1. Decision 1 will give you the cost of 5 or 6 or 9. Now, what is the better number here? Well, as I said, the smaller is the better one, so 5 is the best. So 9 is the worst, 6 is better than 9, but 5 is the lowest one, so it's the best. So out of 5, 6, and 9, the best is 5. Same thing here. Out of 3, 11, and 9, the best number is 3, because that's the smallest. And out of 1, 8, and 13, the best number is 1, because that's the lowest cost. And after you get the best out of the best of each decision, now what optimistic means is now you look for the best of these best. And again, best means lower number. Don't get confused, it's smaller. So 1 is better than 3, and 3 is better than 5. So among these, the best one is 1. So that's your optimistic approach. Optimistic, so in optimistic approach, D3 will be your result. Now, what would be the company's decision if it takes the conservative approach? Same thing. Conservative looks for the worst case scenario. It's always preparing for the worst. That's what conservative means. And for the 3 decisions, let's try to find the worst case scenario for each. So first, decision 1, it's 5, 6, 9. The worst case scenario is when you have to pay the most. Paying 9, I mean, if it helps you, think about millions of dollars. So paying $9 million sounds much worse than paying $5 million. So 9 is the worst of these 3. So we put 9 as the worst. 3, 11, 9. Paying 11 million is the worst of all these 3 numbers, so we put 11. And then out of 1, 8, 13, paying 13 is the worst. So you have 9 and 11, 13. And conservative looks for the best worst case scenario. So out of all the worst case scenarios, it looks for the best of those. And in our case, this is D1. So this is the conservative one, and therefore the decision for conservative approach would be D1. Okay, hopefully that wasn't too confusing, because now we're about to do something harder, which is the regret table for the cost case. Alright, so regret table. Regret is about regret of your decision. I have to say this several times. It's the regret of your decision, not regret of your state of nature. State of nature is not something you could control, so you don't have any regrets over that. You're regretting your decision. So what you want to do is to find the regret for each state of nature. So for each state of nature, you look at the 3 decisions and say who made the best decision, and then for the other people who didn't make the right decision, write their regret. Okay, so out of the 3 decisions, D1, D2, D3, for state of nature 1, you have 5, 3, 1. Who made the best decision? Remember, this is cost. For cost, the lesser number wins. So 1 is the lowest number, so he made the best decision. So what's his regret? He has 0 regret. The person who made the best decision has 0 regret. Okay, so always go for the best decision, look for that, and put 0 for that. Now, the regret for other decisions will be the difference between the best guy's decision. So D2 has 3 as the number. The difference between 3 and 1. 1 is the best decision. 3 and 1 is 2. So D2's regret is 2, whereas D1's regret is 4. For S2, the best decision is 0. The best decision is D2. So I get confused too. Sorry, this is not good. Yeah. What's the best decision again? It's the lowest number. The lowest number is the best decision. So 6, 11, 8. The best number here is 0 because that's the lowest number. Best is the lowest. Okay. Then now you take the differences. 6 and 11 has a difference of 5. And then 6 and 8 has the difference of 2. So 5 and 2 are the regret of D2 and D3. Okay. Now S3. 9 is the best decision because 9 is the lowest number. In this case, you have 2 people making the right decision. Both D1 and D2 have 0 as their regret, whereas 13 has the difference of 4 with the best decision, so this will be the regret of 4. Now, once you calculate these regret, what you do is you write down the maximum regret, meaning you find the maximum regret for each decision. So D1 has the regret of 4. D2 has the max regret of 5. D3 has the maximum regret of 4. Okay. And once you have that, then the minimum regret approach looks at the maximum regret and it tries to minimize the max regret. In this case, you have 2 possible answers. So you should write them both. So they're both minimum max regret approach, and therefore you should write D1 and D3. Both D1 and D3 are the best decision according to minimum regret approach. Okay. Now what's less confusing is the expectation value approach. You want to, let's say you're given the probability of each state of nature. So the probability of S1 happening is 0.3, S2 happening is 0.1, S3 happening is 0.6. In that case, we can calculate the EV of each decision. Remember, expectation value is the outcome times the probability. So EV of D1 will be outcome 5 times the probability 0.3 plus outcome 6, and this time the probability is 0.1, plus outcome 9 times the probability 0.6, and then this will be 1.5, 0.6, and 5.4. 5.4 plus 0.6 is 6, 6 plus 1.5 is 7.5. Okay. EVD2, 3 times 0.3 is 3 and 11 and 9 with probably 0.3, 0.1, 0.6. So you just keep multiplying the outcome by its probability, outcome 9 by its probability, and that gives you 0.9 plus 1.1 plus 5.4. These two add up to 2. So 2 plus 5.4, that's 7.4. EV D3 is 1 times 0.3 plus 8 times 0.1, 8 times 0.1. 13 times 0.6. That's 0.3, 0.8. Let's see, 18, 7.8. Okay, so that's 13 times 0.6 is 7.8. This is 1.1 added to this, you get 8.9. Okay, so we get these expectation values. Now, which one should we choose according to the expectation value approach? Remember, this is cost. So this is where you have to remember that the lower number is the best. The lowest number out of 7.5, 7.4, 8.9 is 7.4. So that's your expectation value approach. So according to expectation value approach, you should choose D2. Okay, finally, let's calculate the expectation value with perfect information, and then let's calculate expectation value of perfect information like before. We're going to use the same probability as before, as 0.3, 0.1, 0.6, 0.3, 0.1, 0.6. Okay, now the expectation value with perfect information is about what would the company do if it gets hold of the information right before it makes the decision. So first, the probability of S1 happening is 0.3. What will be the outcome in that case? Well, out of 5, 3, and 1, remember it's a cost. So which one it would go with? It would go with the lowest number, so it's 1. So you do 1 times 0.3. Plus, the probability of S2 happening is 0.1. And out of 6 and 11 and 8, 6 is the lowest number, so it goes with 6. And then out of 9 and 13, at probably 0.6, it will go with 9 because 9 is the lowest number. Okay, if we calculate this is 0.3, 0.6, and this is 5.4. These adds up to 6 plus 0.3, that's 6.3. Okay, then we use the formula that EVPI is the maximum, the absolute value of EVWPI minus EVWOPI. Remember, the EVWOPI is actually the expectation value you got here. That's 7.4. So this is 7.4. Okay, in the previous slide here, we got the 7.4 as the expectation value of the second decision, right? So that's 7.4. Now, EVWPI is 6.3, and the expectation value of the perfect information is defined as the difference between expectation value with perfect information minus expectation value without perfect information. And since differences are always positive, that's why you have this absolute value here. If you're wondering why we needed this absolute value, it's because even for the cost case, usually in the profit case, EVWPI will be always bigger than EVWPI. So in the profit case, you don't need to have this absolute value. But when the table is giving you the cost, then EVWPI will be lesser than EVWPI, so you need this absolute value so that you get a positive number. So what is 6.3 minus 7.4? That's negative 1.1, but with the absolute value is positive 1.1. So EVPI would be 1.1. So that's how you handle the cost table.